So one of the things I wanted to do is give you a demo of a Fabry Perot cavity. This is a commercial guy. It uses a confocal geometry. And let's see, I think maybe the best thing to do would be use the overhead, Christy, to okay. So here's the laser beam. Okay, and Christy, don't forget to change the back monitor to the overhead camera. Thank you. So here's the laser beam, and you don't have to zoom back out a little bit. It's just a standard helium neon laser, nothing really special about it. And zoom out a little bit more, please. And then over here is the Fabry Perot cavity. Over here is the electronics box to drive the piezoelectric transducer and to amplify the signal from the detector in the back of the Fabry Perot. And this is just an oscilloscope to display the drive signal to the PZT, okay, and the current changed into voltage from the detector. And this is the detector over here, the Fabry Perot cavity. And so let's go ahead and zoom in on that, please, Christy. And here. See, it's a small little guy. Okay. I can't remember what the physical length of the cavity is in here, but it's on the order of a centimeter or two. And there's just a little opening in the front for the light to go in with a little iris. You close down the iris to align the beam into the cavity, and then you use these tip and tilt knobs to optimize the pattern on the detector. What you're doing there is you're just centering up that HeNe fringe pattern on the M equal maximum center fringe. Okay? And so what happens is the PZT changes one of the mirror spacings very slightly, only on the order of several microns. And it does that repetitively. And the pattern I have set up here is a sawtooth pattern, so it'll move linearly in one direction, then snap back, and move one direction and snap back. And so that's what we'll see on the screen. So now if we pan over to the oscilloscope, this way, very good. Okay, now I want to tip this up so you can see it a little better, hopefully. Get some of the cables out of the way, just hold it. And Christy, if you could zoom in on that, I might have to turn down the lights. Okay, so no, it was good, better the way you had it. All right, I'll move this a little bit. There we go. Okay, so what you can see here are multiple peaks. And let me take out the time scale just a little bit to show you. This sawtooth thing, that is the drive signal. Okay? And each set of peaks is separated by one free spectral range. Okay? And inside the free spectral range is the mode pattern of the laser. And you can see 1, 2, 3, maybe 4 peaks there in the laser. Now, why is it behaving like this? Why are the modes changing around so much? By the way, okay, if this is a 10 gigahertz cavity, let's do that problem first. It's 10 gigahertz from here to here. Okay, so the mode spacing, the transverse mode spacing in the laser is much less than a gigahertz. Okay, it's only a fraction of a gigahertz, maybe a couple hundred megahertz. So it's probably about 400 megahertz. So the mode spacing is determined by the length of the laser cavity. Okay, that's that C over 2NL that we went over last time. Okay, and the free spectral range of this is determined by the length of the Fabry Perot cavity. Okay, and if you look, actually let's back out for a second there, Christy, and look at the whole setup. You can see that the Fabry Perot cavity is very, very small compared, let's go ahead and back out so we see the whole laser. Compared to the laser, length of the laser cavity. Okay? So that's why this mode spacing, back to the... I am making you work today. I said it would be an easy day. Sorry. So that's why this mode spacing is much less than the free spectral range of the cavity. Okay? So the cavity is increasing, then off the screen here it goes back down. So these are all separated. The cavity is moving in one direction, and these looks like 3 or 4 different free spectral ranges in the range of the movement here. So, but why are the modes changing around? I mean, it's not really stabilizing. They're jumping around quite a bit. Why is that? Exactly. The laser cavity was just turned on, okay? And you can see that the cavity is changing its length a little bit just due to equalizing the temperature of the components inside. So it takes a little while to stabilize, half an hour, for that to stabilize. Until that time, that cavity is actually moving a little bit. And that will change the mode distribution, the transverse mode distribution in the cavity, because remember, each mode is only spaced by half wavelength in cavity length. So it can jump around quite a bit until the laser stabilizes. Okay. So your single wavelength helium neon laser is not actually single wavelength. Usually. Yeah, it takes a lot of work to actually stabilize the laser cavity. They're very expensive if you actually just want one mode, one longitudinal mode out of it. Okay. Any questions?